We are members of the Toolchain team, and we are going to present you some of the advanced features of our CI system, some of which have already been briefly presented in the previous presentation by Maxime. So this is Thiago, Laurent, and Christophe. And Thiago, you are mainly GDB developer, also CI contributor. Laurent is main CI engineer, and I am mostly a GCC developer and CI contributor. Shall we move? Yes. So here are the topics we are going to cover during this presentation. If we manage to move to the next slide. Okay, so the first item will be presented to you by Thiago about how we manage flaky tests. The next topic will be how we manage the fact that the toolchain is composed of several components, as we said, binutils, GCC, GDB, and how we manage this fact. Then there will be a whole chapter on the pre-commit CI. And finally, we'll conclude with some statistics and feedback from the community. So, Thiago.
Okay, hello. So sorry for the setup problems and for the gloomy background there. Hope it will be a happier talk. As he said, we have these separate modules of the presentation, and we would like to suggest question time at the end of each module. So this first one, flaky tests, then at the end of the flaky tests part, we can take questions on that and so on. This is what was being previously discussed in the previous presentation. So what are flaky tests? You run the test once, you get one result, either pass or fail or unresolved. And then you run it again without changing anything, and you get a different result. And that's very bad because, well, you have a failure, so you have to investigate, see what's going on, and turns out it's nothing, so you wasted time. Both our time as CI maintainers and also the time of developers if we sent a notification to them, or if they are on their own machine running the test suite and they're trying to figure out if their new patch is, I don't know, breaking something. And it also, and actually maybe it's even a bigger problem, it erodes confidence in the test suite results. So over time, people will pay less attention to regressions, and it takes time to rebuild that trust. So we try to deal with that. There are several approaches. So, well, first, what causes flaky tests in our projects? As Christophe was saying, like, we have several sources of problems. So in GDB, which is the one I know more about, a common source of problem is the test case itself. It can have race conditions between the test case and the GDB process that it is driving. So sometimes the test is not very careful in checking the output of GDB, and it loses track of where in the test execution it is. So if the machine is too slow, it can get confused. So sometimes you get failures or not, depending on that. Deja GNU had some issues, and some were fixed, some not. It also has, it uses expect underneath, and another issue in GDB that happens sometimes is expect has a 2 kilobytes buffer for storing the output of GDB, and if tests has to be written with that in mind, because sometimes GDB generates a lot of output, and if it's more than 2 kilobytes, which can happen, the test will not see the output it is expecting because it didn't fit the buffer. It was removed for new output, and that can also be flaky. Sometimes it can happen, sometimes not. And also, like, if a test is stable on hardware, it can be flaky on emulation or vice versa. So these are some kinds of the issues that we see. And to deal with that, there are a few possible ways. We tried reducing parallelism, but that doesn't work. It helps because some of the sources of flakiness is because of concurrency in the machine, but sometimes it's something else. So reducing parallelism, we do that, and especially for GDB test runs, and it helps, but it's not enough. We can remove our X-fail flaky tests. X-fail means basically ignore the failures, and this is a bit hard to do because you have to convince the upstream community, like, we should remove this test, it's not worth it, or convince them, like, this test, we should add an X-fail mark to it, and you have to argue, and then you lose that test, basically. So also not an ideal approach. So we chose this one, create and maintain a list of flaky tests, but we do it automatically. So in the next slides, I'll mention how we detected the flaky tests in our CI. And when we do that, we have a list of flaky tests that the CI maintains automatically, which allows us to ignore failures in those tests. We don't want to ignore forever because maybe someone in the future will fix the test, or maybe we get a new machine where the test is stable. So we add expiration date to the flaky test entry, and so when the entry expires, we start paying attention to that test again, and maybe it will still be flaky or maybe not. So this is how it works. Sorry, one last thing I wanted to comment here about these is that the GNU projects, their test suites have flaky tests since decades, and it has been a big problem in trying to automate CI loops. And when we saw that we could use this approach, we were very happy that it worked, and it's really a boost to the usefulness of the test suite and the results that we got. So how does it work? So we run the test suite normally, or actually the CI. This is all in the CI system automatically. So the CI system runs the test suite on a given commit with a given configuration, as Maxime was mentioning before. So you get the results file, and we compare it against the two artifacts that we have. So we have, from the baseline, we have a list of expected failures that unfortunately it's very rare for a test suite run to have 0 failures, so there's always failures that we live with. And then also there's a list of flaky tests that we have from earlier runs. And in the first run of a configuration, the list of flaky tests will be 0, but that's not a big problem because, as you see during these steps, we will build a list of flaky tests, and that list will be updated in the following CI jobs. Okay, so now we have the results file, we have the expected failures, the flaky tests. So with that, we can filter out expected fails. We don't care about those. We filter out flaky tests. If there's a fail in the results that is also in the flaky tests, we can also ignore that, filter out. And what's left of failures, we call them unexpected failures. So if we have any, we will run the test suite again. And that's because we are not sure whether the new fail is a real regression or whether it's just a flaky test that we didn't know about and is causing problems. So we can run only the subset of the test suite that contains those failures. We don't have to run everything again. And in the second run, if we do that again in the second run, like if new tests are still failing, well, we know this. Sorry, I got a bit confused, but like when we get the results from the second run, if the same failures we had in the first are still failing, then we are confident that it's a real failure and it's a regression, and we create a Jira card, report it. And if the failure of the previous run is not present anymore, so we have just detected a flaky test and we add it to the flaky test list. And then we keep doing this in this loop until all the test suite results are either expected or flaky. So eventually the CI job finishes because there are no unexpected failures anymore. So we've seen for GDB when we don't have a flaky test list, you can run, I don't know, 6 or even 10 times, 20. Okay, and now when we have a good flaky test list, sometimes just the first run is enough, or sometimes you need 2 runs. So this is an example of this happening. Like this is a subset of the output of the CI loop, and it shows this process. So for instance, we can see here that we have a flaky test list from the baseline and also an expected failures list from the baseline. And in this, so we run the test suite the first time. So for this example, we have a failure 1 and failure 2 that is not, neither of those is in those files. So we want to see whether they are real failures or not. So we run the test suite again with just the test cases that contain these tests. And in this example, we have a test, the first one passed, so it's flaky. And then we add to the flaky.xfail file, and we add an expiration date. After this date, we will start paying attention to this again. Until then, we are not. And the second failure happened again, so this is a regression, and we will open a Jira card and we will send a notification email. So because we had unexpected results in this run, we will do a second run. And for the purposes of this example, I put like surprise new failure that didn't happen before. So starting from run 2, every new fail, we can know that it's not a regression, it's a flaky test, because if it was a real regression, it would have appeared in the first 2 runs as well. So starting from this run, everything that shows up here will go to the flaky file, and we will keep running new instances of the test suite until we don't get any new failures. So this is it. And one thing I wanted to mention is that we actually, when doing this, a little bit before it expires, we pretend that we are in the future and the entry already expired, so that we can redetect this before they actually expire, so that we don't have a time so that we don't send a false positive email in case the failure is still real. So we have a period of a few weeks when we detect failures, flaky tests, and try to anticipate before they expire. Okay, thank you. So yeah, this is just an illustration. Maxine showed a lot of those, so I'll just mention quickly here. We have here the red is total number of tests. It's a bit surprising, but it's actually expected that GDB has a fluctuating number of total tests run. It doesn't fluctuate a lot. It's around 116,000 tests, and more or less, I don't know, a few hundreds. And the green is failures. So when it goes down, it's improvements. And you can see that this is stable failures already filtering out the flaky failures. So you can see that it's stable, and each of these steps is a regression. And the blue line is number of flaky tests, entries in the flaky file. So as time goes on, we detect more and more flaky tests. So yeah, this is the end of my part. So are there any questions? Okay, thank you.
Hello. So we'll be discussing on how multiple components are handled in our CI. In classic CI, we as Maxime said, toolchain is composed of many components: the binutils, GCC, GDB debugger, and glibc, and so on. Typical usual tests are building the component, using the test suite of this component, and comparing to the baseline results. This is very important because the test suite has been designed by the developer, and it covers all the tests, all the pieces it wants to, and eventually some Bugzilla to cover the corner case. But it's limited to the component. But we know that all the components of the toolchain are interrelated, are tightly coupled, and when having a change in binutils, it can impact the debugger, it can impact the GCC, and all the change in one component have an impact on the others. And moreover, in feature development, we often can see some developments that have one part in binutils and one part in GCC, and so it all goes together, and it makes sense to test them together. So in our CI, as Maxime said, we are updating, in previous presentation, we are updating all the components together to the main line. And we are updating once every few days. binutils component, GCC, glibc, also the debugger, but also the Linux header and also the simulator. We are building a toolchain with fully updated components. What else? As previously, we are testing this one. The toolchain is built against the test suite of each one of the components, the binutils test suite and so on. And if there's no regression, we are storing it as a new baseline. And if there's a regression, we have to find which component has caused the regression and which commit has caused the regression. And that's it. So so this is an overview of the steps of one of our build. We can see that we are building the full toolchain with the bootstrap, even the Linux kernel header, building the simulator, testing the GCC test suite, and checking the regression. In some other job, we are testing the binutils test suite. So this is why it doesn't appear on this job. What else? I think that's it. Okay. A quick slide to show how we find the guilty component and then the guilty commit that cause the regression. So in this example, let's suppose build n-1 was the baseline and it was successful, and this is the baseline. In the current build, we are updating all the components, and let's suppose we are finding a regression. Then the first thing is to find which component has caused this regression. So we are keeping the same GCC, not updating it, and updating all the rest, for instance. And then in the example I have written, this job passed correctly and doesn't show any regression. In the second build, we are updating the GCC to the tip of trunk, but not the other. And this one is failing, so that means the regression is caused by the up-to-date GCC. And then starting from here, we are bisecting to pinpoint the exact commit to be able to report and to store in Jira card and so on. So few interesting cases to show that this cross-component testing is not purely theoretical and is useful. I've selected two reports that we have created, find. The first one was caused by a binutils commit and caused a regression in glibc test suite. As first sight, the commit doesn't have any link to the failure in glibc test suite, but in fact it has a link, and it has been reported to the author of the patch, and it has been fixed in binutils. So the glibc test suite has went back to the normal state, let's say. I wanted to add that this kind of issue is usually lately found when integrating the latest binutils and latest glibc in the release, and and having it very early makes the fix more easy to be done. Okay. The second one appeared in the GCC test suite and is caused by the GDB commit in the libstd++ test case. It appeared to be, well, okay. This email has been automatically sent to the author of the patch of the GDB committer. We can see that this is the JIRA card created. This is the commit that has been identified to cause the regression. The regression are printed there. Please have a look and let us know if you are working on it. So starting from this email, a discussion started between the GDB committer and the libstd++ maintainers. And in this example, it revealed a long-standing issue in GDB component, and it has been chosen to work around the test case. But whatever the issue, whatever it is important for us to detect and report quickly to the community. That's it on my part. Do you have any question? Okay. Another.
So let's start with a new chapter about pre-commit CI. So what is pre-commit CI? In fact, the idea is just that instead of just catching regressions, that is problem which have been committed and introduced in the toolchain, why not try to avoid them in the first place? So the idea is to test the patches as soon as they are posted on the mailing list. And in addition to avoiding regressions, also it's a useful feature for the component reviewers and maintainers, because if they know that the patch broke CI or passed the tests, it gives them useful information to comment on the patch. This is quite different in implementation from post-commit CI, because in post-commit CI, you can extract the patches from the Git repositories. So you can just update your baseline up to the current point, build and run the test and do the usual CI loop. With pre-commit CI, we have to somehow grab the patches on the lists, extract them, apply them, and then do the usual stuff. How we do that, how we chose to do that, we are using a patchwork instance, which is a service run by the Sourceware team. Patchwork is a system which monitors mailing lists and indexes the mails, and it can be used to browse the current status of the various patches. But it also has an API which we can use to interact with it and download patches and do what we want with them. So what we do, we fetch patches from Patchwork, we apply them on top of the current baseline for that CI loop, and then after that we run the very same build and testing procedure that we do for post-commit CI. After that, once we get the results of the check step, where we check if there is any regression, we update the status of the patch on patchwork with either a green or a red flag, and we notify the patch author in case of a problem. So here is a screenshot of how patchwork looks like. In the middle, you can see the title of the patch series. On the left is the patch titles. So in general, it's a one-on-one mapping. But if you have a patch series which is composed of several patches, like is the case here, you can see that the title is the title of the first one in both cases for the series. But here we have two different patches. What is of interest to us in this screenshot are the green, red, and orange bullets here, which correspond to the number of successful warning of failures from build bots. I would say that we are not the only one to use patchwork. There are other build bots which are running. Some are from Red Hat. Also, I think there are some from the RISC-V community. I'm not sure who runs them. I can show you an example of when you click on one of these patches. Yes, I'm not sure which one was selected here, but you can see that you have the details that in this case we have 3 of the build bots which were successful and 1 which failed. What we can notice here that we have 2 flavors of bots, one which is build, one which is check. So in the build one, we just check that the toolchain builds, and the check ones actually run some tests. So what we can see here is that, well, the testing was successful on AR64, but not on AR32. As we said earlier, AR62 seems to be a bit less popular these days, so it's less well tested and less attended. I would like to mention also that patchwork is used by some of the toolchain maintainers. For instance, the ARM maintainers, Richard Earnshaw, Richard Sandiford, use this dashboard and a variant which is restricted to only the patches which they are currently reviewing, and they do pay attention to these bots. So what additional challenge do we have to address with pre-commit CI? As I mentioned earlier, we have to grab the patches from the mailing list, so we have some problems that it's not always straightforward to extract the patch because the mails can be incorrectly formatted. So in that case, what will happen is that patchwork will not recognize the patch as a patch, and so we won't grab anything. So that's a case where we just do nothing. There are also other cases when people send several patch series which have implicit dependencies. So for instance, you have a patch series to enable feature 1, another one to enable feature 2, and the second one in fact depends on feature 1. When we are going to test the patch for feature 2, we don't have the information that we should also have applied feature 1, so this is going to fail. So this is another possible improvement area. On a different aspect, we also have to be careful about potential attacks in the sense that such patches are less trusted, much less trusted than what has been committed. Although recently, as we saw with the XV or XZ vulnerability, some commits have actually been proven to be wrong. But we do take some special and additional measures to avoid problems and leaks with our system. Finally, it's really important to mention that we have a bandwidth problem to address, because as Maxime explained in the previous presentation, with post-commit CI, we can update baseline every several days maybe, and just move forward by several dozens or hundreds of commits. If everything is okay, we update the baseline. And this means that in a single build, we have moved forward for that many commits. In pre-commit CI, of course, we want to test every single patch. And so every single patch, we have to run a full build. So this means that when, for instance, when GCC is under heavy development phase, that is known as stage 1, the number of patches posted every day is really, really large. So we are starting to see stage 1 has reopened a couple of weeks ago, so we'll see how well we manage. Now, a few words on how our system was received by the upstream community. So when we first started it, we got some positive feedback, but also some complaints because the reports were not providing the information people were expecting. So although we had positive messages, we also had a few grumpy people saying, "Oh, this is useless, I don't find what I want." So we worked on improving the notification messages, and things improved. Then we presented the whole system at large during the last GNU Cauldron conference in September, I think. Yes, it was in Cambridge. And these presentations were highly successful. People were very welcoming of that system. And this made it more obvious to the community that we were running that for real. And after that, we noticed that we got more inputs from the community, more positive feedback. So that was good for us, and it helped us improve it further. We noticed that the Linaro CI, between quotes, was almost used as a brand in some of the messages exchanged by people on the list saying, "Oh, Linaro CI found a problem with your patches or with my patches," and it was interesting to see this naming appear. Now we are at a stage where we don't get any more complaints, I think. I haven't seen any in a while, and now people are starting to request more features. So that is, could you support this or that? And for example, if we could automatically check coding style issues, changelog format, etc., as an help for the maintainers and reviewers, that these basic things can be automatically tested. A few other things we noticed with interacting with the upstream community is that in some cases it seems that people do not pay attention to our report. So we try to improve that by improving the message in the notification, and as we said earlier, we also contact the authors directly and try to put the community into action around that. What we are considering is maybe we should reply directly on the mailing list so that it's more obvious that a patch is breaking something, and that because in pre-commit CI, unlike post-commit CI, currently the notification of regression is only sent to the patch author, not to the list. Maybe if we include the list in the distribution, this will make other reviewers and contributors more aware that a patch under review is a potential issue. We are also considering maybe making it easier in the policy to revert changes. For instance, in the LLVM community, reverting a patch which is causing problems is a very common practice. It's not the case at all in the GNU toolchain. So maybe that's also another possible improvement. And I mentioned this possibility of changing the project policy because we had a case recently where we managed to change the policy. In the GNU projects, you may know that some files present in the source tree are actually generated from master files. So there are the well-known AutoTools file, but there are other sources, other types of files like that. For instance, in binutils and GDB, we have the opcodes, so that these are huge tables which are automatically generated from some master files. And the policy is that normally we don't, the patch submitter, we don't include the changes to the master files. So what happens is that the CI does not have a full view of the actual patch, and we cannot test what is supposed to be tested. So we try to address that automatically, but it was not possible to do that. So what we propose is actually a policy change to ask people to send the full patch. And this was more than accepted. It was welcomed by several maintainers who actually said, oh yes, it will give us more confidence that what people are going to commit is right, because sometimes it did happen that people committed files with wrongly regenerated files. So now we are going to show you, well, maybe you have some questions?
Can you please describe what is or what will be the pricing model for Precommit CI?
The pricing model?
Model, yeah. Like based on what the pricing will be set up.
Maybe that's a question for Maxim.
These are engineers from Microsoft. Welcome them. The pricing model is going to be per configuration. So, for example, we can support, as you have seen, the overhead of testing in pre-commit is quite substantial. And the pricing model there will be how many configurations, so essentially how many different CI loops we are going to track. And our goal is to have that as a fraction of what it would take for a maintainer to do this in his or just by spending his or her engineering time. So the automation should cut down the effort by 2, 3, 4 times. Let's talk more offline.
Any other question? No? So, Thiago, will you show us some statistic?
Yeah, okay, so yeah, we have a bit of time. Thank you. So we collected some statistics from what we've done so far. This is actually the less interesting graph. So this is number of notification emails per month. So far, we started in August, and we prepared these slides in March, end of March. So August is not a full month, and we were ramping up in September. We stabilized more or less around 150. It's just absolute numbers, not so interesting as the curve. So we see a slowdown in activity in the holidays, and in March, GCC was in stage 4. So it makes sense that the patches that were sent to the mailing list don't have so many problems. That's good news. So this is an interesting one. What happened was Christoph was overlooking the CI to check everything was good. And he noticed during November last year that suddenly he started getting a lot of post-commit regressions, and we digged into it, and it turns out that we accidentally broke the pre-commit CI for 2 weeks, and it was broken from the beginning of week 45, which is beginning of November of 2023, and beginning of week 47, which is more to the end of November. So we can see here, and this y-axis is the number of regressions that were committed in the repo. So number of Jira cards for commits in upstream. So we can see that we had a jump of regressions after we accidentally stopped checking patches. So it was nice to see that the pre-commit CI is having a good effect. And we actually can see, like, this is, I think, 9 maybe, and this is like 19, so 10 regressions. In a period of, sorry?
That's about 1 per day.
Yes, more or less one regression per day that we were avoiding. We avoid with the pre-commit CI, and we stopped avoiding when we broke it.
May I also make a note on this slide? Is that 47 week 47? This is what was happening every week before we enabled pre-commit CI. And this is what is happening on all other architectures which do not have pre-commit CI currently,
yes.
Every week.
I think this also coincides with like end of stage 1 and stage 3, which is also where we see most of the regression. Now, I'm not saying it's not helping, it definitely is, but you also need to take that into consideration. It's not.
Yeah, actually it was end of, yes, stage 1, I remember that.
Yeah.
And yes, I was impressed to see that many regression reports just coming precisely at that point. I was, yes, feeling there was a rush of people forcing to commit. Oh, yes, it's almost working.
Yeah. we can fix it later. At least let's get it in.
Nice.
Sorry, still very impressive, by the way, not to take away from it.
Thank you. Yeah, thank you for the comments. So this is interesting. Now I'm going to post-commit statistics. This is total, since we started this until we finished the slides, total number of regressions detected in upstream repository for each project. So we can see that GCC has more. It makes sense, like it's the bigger project, more active. And the thing that's interesting here is that for all projects, ARM has more regressions than AArch64. So ARM here is 32-bit ARM, AArch32 specifically. So yeah, this shows that developers are more focused nowadays on 64-bit. And ARM also has another interesting thing that we noticed is that ARM also serves as the canary in the coal mine for all 32-bit architecture. So we catch regressions not only that are ARM specific here, but also regressions that are for 32-bit architectures in general. So there's that. And here is a different visualization of the same issue. Like this is still number of post-commit regressions detected for each month. Each color is one project. And we can see here as well the spike in November. And it works out to the same, more or less the same number of avoided regressions per day when compared to the other months. So it's an interesting effect of the...
One comment, GNU Toolchain community is very consistent. If you account that December is holidays, and you would, if it was not holidays, it would grow a little bit. It's like a straight line. The closer we are to the release, the less regression. So that's very, very consistent.
Yeah. So we like to end this with some selected quotes from the mailing lists. I'll just leave it here. So people have provided an unsolicited positive praise, and we were happy to get them and put them on a slide in a presentation. So thank you for the reception to the community of the projects. And I would like to end with an apology to Roger Sale for ruining his New Year's Eve. I hope he had a good New Year's Eve, despite our email notification. So, are there any questions, any comments? Okay, thank you very much.